Welcome to the next lesson in this module, which focuses on Java support for exception handling, which involves both an extensible hierarchy of classes and a set of virtual machine mechanisms that separate the control flow paths of normal app execution from the control flow paths of anomalous app execution. After completing this lesson, you'll know why exceptions are needed to make Java apps more robust and easier to understand and evolve. You'll also understand how exceptions are reported and handled in Java apps. Finally, you'll recognize the two main types of exceptions that are supported via Java's hierarchy of exception subclasses.
Despite our best efforts, apps will occasionally encounter problems that just can't be ignored. Echoing the classic Murphy's Law, anything that can go wrong will go wrong. For example, problems can arise when an app attempts to open a file that is not available on the device, or tries to call a method or access a field via a null reference, or indexes into an array before or after the valid range of the array. To provide a nicely structured way of dealing with these types of problems, Java provides an exception handling mechanism that enables the logic of an app to differ in a structured way, so the control flow paths of normal app execution is clearly and cleanly separated from the control flow paths of anomalous app execution. Exceptions in Java are supported by both an extensible hierarchy of classes and a set of mechanisms provided by the underlying virtual machine that systematically handle problems arising during the execution of an app. If an error condition occurs in a block of Java code in an app, that block can throw an exception to notify another part of the app that a problem has occurred. This notification allows the part of the app that catches the exception to take the appropriate action in response, which may include interacting with the user to fix the problem, logging the problem, or exiting the app altogether. Any code can report the occurrence of an error condition by calling throw with the appropriate instance of an exception class. For example, if the initial capacity passed to the vector constructor is less than 0, a new illegal argument exception object can be thrown to the portion of code that tried to create a vector erroneously. Likewise, if the index value passed to vector's last index of method is beyond the bounds of the vector, then a new index out of bounds exception object is thrown. When an exception is thrown, the virtual machine performs a number of steps. For example, consider an app with a group of methods that are called in a particular order, where method 1 calls method 2, which performs some computations, and then calls method 3, which in turn performs other computations, and ultimately calls method 4. Let's assume that method 4 throws an I/O exception, which can occur under various circumstances, such as trying to write a downloaded image to a file when there's no space available on the storage device. When method 4 throws the I/O exception, normal program execution stops. Control then transfers to the appropriate exception handler, which may involve the virtual machine searching up the runtime call stack to find an appropriate handler for the I/O exception. For the sake of discussion, we'll have method 1 catch the I/O exception and perform the appropriate action, such as informing the user that the storage device is full. The Java language provides some syntax for handling exceptions. A try block contains a sequence of one or more statements that encloses a region of code that may throw exceptions. For example, this try block encloses a statement that defines a vector of strings. This vector is passed a negative number as its initial capacity, which of course is an error. One or more catch blocks can be associated with a try block. A catch block defines an exception handler that handles the type of exception indicated by its argument. For example, this catch block handles the illegal argument exception thrown by the vector constructor when it is past an initial capacity less than 0. Another syntactic element associated with Java exceptions is the finally block, which always runs no matter how the try block is exited. For example, this finally block is always run to unlock the lock, regardless of whether the statements within the try block throw an exception or if the try block returns from the method. Yet another syntactic element associated with Java exceptions is the try with resources block, which was introduced in Java 7. This variant of a try lock declares one or more resources that will be closed automatically after the app's flow of control exits the block. For example, this try with resources block defines a variable called buffReader, which is used within the block to read a new line. The close method of the buffReader variable is automatically closed when the try with resources block exits, thereby ensuring that any resources it allocates are released. Java exceptions are organized into a class hierarchy, all of which inherit from the exception superclass. Handlers can be specified for different subclasses of exception. For example, a try block could be followed by 2 catch blocks, one for the index out of bounds exception and another for the illegal argument exception, both of which are descendants of the exception superclass. If a method doesn't specify a handler for an exception that's thrown, the next matching handler up the runtime stack gets called. For example, method 1 calls method 2 within a try block. Method 2 then calls method 3 without using a try block, so it has no way to handle any exceptions method 3 may throw. Therefore, if method 3 throws some exception, it won't be handled in method 2, but instead will be handled back in method 1's catch block, which handles some exception. To handle every possible type of exception in a method, simply define a catch block that handles exception, which, as a superclass, forms the base of the Java exception inheritance hierarchy. Moreover, to handle every possible type of error, define a catch block that handles throwable, which is the superclass of all recoverable runtime errors and exceptions in the Java language. A useful method defined by throwable, and thus available to all exception subclasses, is print stack trace, which prints a backtrace of all methods on the runtime stack leading up to the location where the exception occurred. This backtrace can be extremely helpful when locating bugs in your apps. There are 2 general types of exceptions supported by Java. One type is called checked exceptions. Methods declaring checked exceptions require their callers to provide an exception handler, or else the compiler will flag the calling code as an error. For example, the writeObject method in the vector class explicitly declares that it may throw the I/O exception. Therefore, if method 1 calls the writeObject method on a vector object, it must contain a catch block that catches the I/O exception. The second general type of exception supported by Java is called an unchecked exception, which can be thrown by a method without it having explicitly declared the exception in its signature. For example, method A can throw an unchecked exception, such as the index out of bounds exception. Method B can call method A without having to define a catch block for the index out of bounds exception. Moreover, it could define a catch block for a more general exception, such as the exception superclass. In fact, method B could catch the index out of bounds exception as an exception, and then rethrow it as a new runtime exception. Although we've covered quite a bit of material in this lesson, there's still more to learn about Java exceptions, so we recommend you read more about these topics in various online Java resources.
This lesson focused on exception handling in Java, which involves both an extensible hierarchy of classes and a set of virtual machine mechanisms that separate the control flow paths of normal app execution from the control flow paths of anomalous app execution. Now that you've completed this lesson, you should know why exceptions are needed to make Java apps more robust and easier to understand and evolve. You should also now understand how exceptions are reported and handled in Java apps. Finally, you should recognize the two main types of exceptions that are supported via Java's hierarchy of exception subclasses. Even well-written apps occasionally encounter problems that just can't be ignored. So Java's exception handling mechanism provides a nicely structured way of dealing with these problems.